Hi everyone, welcome to my channel. This question has been taken from Resnick and Halliday, chapter 24 related to electrostatics, question number 4, 5 and 6. Question number 4 is here. Two similar tiny balls of mass m are hung from silk threads of length L and carry equal charges Q as shown in the figure 25-22. Assume that theta is so small that tan theta can be replaced by its approximate equal sin theta. A, to this approximation, so that for equilibrium x will be equal to q square by L divided by 2 pi epsilon naught mg, the whole thing to the power 1 by 3, where x is the separation between the balls in equilibrium. If L 122 centimeter, m is equal to 11.2 gram and x is equal to 4.7 centimeter, what is the value of Q? So let us solve this. What is happening here? When the ball was initially hung with the silk threads, these two balls were charged and of the similar kind of charge. So they started separating from each other due to repulsive force, electrostatic repulsive force. And finally, after making a separation of x where both the ball comes to equilibrium. During the equilibrium separation, the angle of the thread attached to both the balls from the vertical was making theta. So when the system is in equilibrium, when the ball is in equilibrium, it means the total force on the ball and the torque is 0. Fe we have shown as electrostatic repulsion force. Mg is the weight of the ball. T is the tension in the thread. L is the length of the silk thread. So if we make the free body diagram of one ball, it will be like this. Vertical we have chosen it as y-axis and the horizontal as x-axis. The whole forces have been shown here. Since this ball is in equilibrium, the total force in the x direction will be 0. That is what is written here. In the x direction, electrostatic force is this, Fe, and a component of the tension force in the thread acting on the ball along the axis will be minus t sine theta in this direction. So Fe minus t sine theta is equal to 0. So we got equation 1. Similarly, for equilibrium, we can write in the y direction also the net force is 0. And we got equation 2, T cos theta is equal to mg. From equation 1 and 2, we can equate mg tan theta is equal to Fa. This is a simple calculation. Now, since tan theta in the question is given that theta is so small that it can be approximated as sine theta, so tan theta we have replaced with sine theta. From the triangle, you can see that sine theta is x by 2 divided by L. So this is written here. Now, Fe is the electrostatic force. So we know that Fe can be written as kq square by x square, where k is 1 by 4 pi epsilon naught. So putting this value in equation 3 and solving, we will get x as q square L divided by 2 pi epsilon naught mg, whole thing in bracket, and the bracket is under the power 1 by 3. So this will be the answer. This we have given the name as number 4 equation. For the part B, you will have to put all the numerical value that is given in the question and you will get the result. So that I have left it on you guys. Calculation or simplifying also I have left it that you should do it and see. So this is your number 4 question. Now we will go back to number 5 question. If the balls of figure 25-22 are conducting, what happens to them after one is discharged? Explain your answer. B. Find the new equilibrium separation. So what is happening when one of the ball will be discharged? Means there is no charge on that. So force of repulsion, that is electrostatic force, will vanish. So ball under the gravitational pull will swing back and it will come in contact with each other. Once it comes in contact with each other, from the other ball which is charged, the charge will start transferring to the ball which has been discharged till the time when the potential of both the ball reaches to equal value. Since the ball is similar, so we can conclude that when the potential reaches to equal on both the ball, q by 2 charge will be on one ball and q by 2 charge will be on the other ball. So this is your part A answer. You can go through. Now we have already calculated or we have already solved for the separation x for any q, that is in equation 4. Only thing now what is changing in this equation is q will become q by 2. So putting that value, we will be the new separation where the ball will come again in equilibrium will be this q square L divided by 8 pi epsilon naught mg in bracket and the whole to the power 1 by 3. Come to the question 6. Assume that each ball in problem 4 is losing charge at the rate of 1.2 Newton Coulomb per second. At what instantaneous relative speed do the ball approach each other initially? So what is given is TQ by TT as 1.2 Newton Coulomb per second. So initial relative speed can be obtained by differentiating equation number 4, that is dx by dt. So dx by dt will be this. Put the value of dq by dt, initial charge q, and L and 2 pi epsilon naught mg. These all value if you put, you will be getting your answer. Only thing you have to take care that all the units, means all the data should be converted to the correct unit and put inside to get the numerical value. So this I have left it on you. So hope you understood how this problem has been solved. If doubt at any point, you can write in comment. I will reply. Thank you.